Hey there, my name is Gokul, and today I'm going to talk about our work on imitation learning in the presence of unobserved confounders. Consider the problem of trying to learn to fly a quadcopter by imitating an expert pilot. Let's assume there's heavy gusts of wind that cause the quadcopter to deviate from the intended straight path of the expert. Now, what will happen if we try to apply a standard imitation learning algorithm like behavioral cloning to the set of demonstrations? Well, the learner is likely to pick up on the correlation that being a little bit on the left is usually followed by going even more left. If they ignore the fact that it was the wind that was the root cause of this correlation, they might attempt to reproduce the swerving behavior of the expert, causing them to deviate even further at test time due to the continued influence of the wind. More abstractly, the effect of a confounder, like the wind in our previous example, is to introduce temporal correlations in the recorded actions that do not have their true cause in the recorded state. We can visualize this effect via a graphical model. At each time step, the expert takes an action responding to the observed state, and the MDP transitions to the next state. The persistent confounder U affects multiple actions. This means when we try to regress from states to actions, standard approaches will produce inconsistent estimates of the expert's policy. This is because the confounding travels through the dynamics to influence the next state, leading to spurious correlations between recorded states and actions. The learner might then latch onto these spurious correlations to explain away the effect of the confounder by misattributing it to some element of the state, leading to poor test time performance. This is what leads to the increased swerving in our quadcopter example. What we'd like to learn instead is a policy that flies as close to straight as the expert does. It turns out we can find such a policy by applying a technique from econometrics called instrumental variable regression. Consider trying to regress from x to y, both of which are influenced by confounder u. Ideally, to mitigate the effect of the confounder, we would randomize over x via a controlled experiment. However, if we only have observational data, we can achieve a similar effect via a source of randomness independent of the confounder. This variable is called an instrument, which we denote as z. The key idea is we can condition on z to counter out the effect of the confounder. In our model, past states act as this instrument, as they are independent of confounding. We can leverage this past state instrument in two ways. The first is a generative modeling approach that utilizes a simulator. The second is a game theoretic approach, which can be performed completely offline. Empirically, we find that both algorithms are able to outperform behavioral cloning on a simulated rocket landing task. Thank you for your time, and please check out our full paper and videos at a link on the screen.